So let's introduce the t-distribution and how and why we need to use it to make confidence intervals. So remember, in this example we did before, in an earlier video, we made a confidence interval for the mean weight of all bricks that come out of a factory. But in order to do that, I had to know this: the standard deviation for weights of all the bricks that come out of the factory. And this is kind of a magic number, because if you knew the standard deviation for all the bricks that came out of the factory, then that would imply that you knew the distribution of weights of bricks for the factory, and then that would mean you know its mean. So why are you estimating its mean from a sample if you already have enough information to know it in the first place? So this is kind of a silly number. What would be nice is if we could make a confidence interval for an unknown parameter just from information in a sample, not using any other parameters of that distribution. Okay? So that's what we're going to do now. But in order to do that, we need, you'll see, to go through this t-distribution. So let's suppose we take a random sample of n values from a normal distribution, and we compute these two things. Compute x bar, which is the mean in our sample, as usual, but then also compute this thing, the variance of our sample. Because I'm going to end up, why am I doing this? Because I want to know the standard deviation in my sample, and I want to replace the standard deviation in the whole population, which I'm never going to know in practice, with the standard deviation for my sample, which I can know because I know the sample values. So take a sample, compute the mean of the sample, and also compute the standard deviation. Well, here I'm computing the variance, but I can square root it and get the standard deviation. So I'll call the standard deviation in the population sigma, and the standard deviation in the sample little s. Okay? So when I come up with this, actually, I should fix something. This should really be a capital S squared, because it's a random variable, right? It depends on which sample we got. So I'll do that to make that clear. So when I compute this standard deviation, sorry, when I compute this variance, and then I'll have to square root it to get the standard deviation. Remember, the variance is the average squared distance from the mean. So I'm going to take the average squared distance from the sample mean. But there's one weird thing in here. I've got n sample values that I'm adding up. Well, I'm taking the difference between each sample value and the mean, squaring it, and adding those up. But then I'm not dividing by n. I'm dividing by n minus 1. And if I was really computing the average squared distance from the mean, I would be dividing by n here. So why divide by n minus 1, not by n? It turns out that if you do that, then this thing will give you an unbiased estimator of the population variance. So this variance of your sample computed this way, with n minus 1 instead of by n, will give you an unbiased estimator of the variance in the population, whereas if you had divided by n, you would in fact get a biased estimator that would systematically underestimate the variance in the population. Okay, and for theoretical reasons we're not going to go into, that ends up being important. So, we take a sample, we compute the sample mean, we compute the sample variance, but using this slightly adjusted formula. If you want to look this up, this is called Bessel's correction. So, if you do that, by the central limit theorem, we know that x bar, the sample mean, this guy is normally distributed. And so if you take this, x bar, which is already normally distributed, you subtract its mean, you divide by its standard deviation, which the central limit theorem tells you, the mean is mu, the standard deviation is sigma over root n, then you get a standard normal random variable. And that's the main fact we used to justify our procedure for making confidence intervals, to derive the formulas for confidence intervals. So now what we would like to do is say, okay, but this sigma, this is a thing that we can't know in general in practice. This is an unknown parameter of the distribution we're sampling from. Could we just, instead of this sigma here, put S, put the standard deviation from our sample, which you can compute, the Bessel corrected standard deviation. So you compute the variance like this, you square root it to get the standard deviation. Could we replace the population standard deviation with the sample standard deviation? That would be really nice. And then you see, if I were to go through justifying this confidence interval, I would go through all the same steps, but instead of a sigma here, there would have been an S, and all the way down, instead of sigmas here, there would be S's, but that's the only thing that would change. My procedure for getting confidence intervals would be exactly the same. I'd just be using my sample standard deviation in place of my population standard deviation, which I don't know. That would be nice. Turns out you can almost do that. The distribution of this thing, though, is not a normal distribution. Turns out that it's this thing, a t-distribution. What is a t-distribution? Okay. Well, if I were to graph a normal distribution with mean 0 and standard deviation 1, it would look, let's do it something like this. I'm going to make it dotted here. All right. So you should imagine this normal distribution as, yeah, sort of this bell-shaped curve. So let's let that be the graph of standard normal random variable, the PDF for a standard normal random variable. What happens with this thing? Well, it turns out that the distribution of this thing, it depends on the sample size. So if you take different sample sizes, you get different looking distributions. If the sample size is small, you'll get a distribution which is lower in the middle, but bigger in the tails. It's going to look something like this. And as the sample size gets bigger and bigger, it gets taller in the middle and lower in the tails. All right. And actually, as the sample size gets bigger and bigger, approaches infinity, in fact, the distribution of this thing right here will approach the standard normal distribution. So for very large sample sizes, the distribution of this thing will be essentially identical to the distribution of this thing. But the actual distribution of this, it's called the t-distribution, and this thing is called the t-statistic. So remember, a statistic is something you can compute from a sample, and yes, indeed, you can compute this, well, assuming you know mu, you can compute this from a sample, and this is called the t-statistic. So let's let t equal that thing, x bar minus mu over s over root n. Let's let b where, yeah, right, where x bar and s are the mean and Bessel corrected standard deviation of our sample. Okay? Sorry, don't need a bracket there. So, as above, from your sample, you can compute the mean, you can compute this Bessel corrected variance, you can square root it to get the standard deviation. Then, the distribution of this thing So this quantity has a t-distribution, it's called t-distribution, with n minus 1 degrees of freedom. So I'm not going to actually write down a formula for the PDF of this distribution because it's a disaster and it depends on n, so additional degree of complexity here. But what you need to know is that there is a name for the distribution of this quantity. It's called the t-distribution with n minus 1 degrees of freedom, where n is your sample size. So remember that the shape of the distribution depends on the size of the sample you're taking. And yeah, if you subtract 1 from that, you get this parameter called the degree of freedom, which changes the shape of this distribution. Okay. Now, all this was assuming that our random sample comes from a normal distribution, and we don't know that in practice. The central limit theorem says we could be sampling from any kind of distribution, and this is still going to turn out to be normal. But the definition of the t-distribution is it's the distribution of this statistic when your sample was taken from a distribution that is known to be normal. So, it turns out, however, that even if you're sampling from a non-normal distribution, if your sample size is sufficiently large, not even that big usually, like even bigger than 15 or 20, then the distribution of this quantity will be very close to the t-distribution. And, so there are some subtleties in here. It is absolutely true that asymptotically, so as the sample size goes to infinity, this distribution, the distribution of this quantity, gets closer and closer to a t-distribution, even if you're sampling from a non-normal population. And this distribution of the regular z's, the regular z-score, is a normal distribution. And so as the sample size goes to infinity, everything ends up, no matter what distribution you're sampling from, and whether you're using the population or the sample standard deviation, it turns out that when your sample size gets really big, both of these things get really close to being standard, normal, random variable. Okay. However, as long as n is finite, the distribution of this thing is not exactly a normal distribution. It just gets closer and closer to a normal distribution. So, in order to deal with this thing, we need a table of values. Like a z table, we need the equivalent thing, a t table. And so, yeah, you can use the t table. If you have a t table, you can use it, and you can do calculations using the t distribution. In particular, you can make confidence intervals using the t distribution, where you're using sample standard deviation, which is a thing you actually can know, in place of the population standard deviation, which is it's very rare that you would actually be in a situation where you would ever know that. So there's a lot of theoretical stuff going on here, but when you actually go to use this, the procedure for constructing a confidence interval is really exactly the same as we had before. When we use the population standard deviation, the only difference is we're using the sample standard deviation in place. And we're using the t-distribution in place of the normal distribution. So let's do an example where we use it. And here you can really see that there's no magic numbers involved, because I'm just going to actually give you the sample values, and we're going to make the confidence interval with nothing else, just knowing only the sample values, no other information. So here it is. Quick example. Given below are the heights of 10 randomly selected students at the college in inches. So here they are, 64 inches, 68 inches, 62 inches. I was able to get a simple random sample of 10 students and measure their heights. That's what I got, suppose. So now we're going to construct a 95% confidence interval for the average height of all students at the college, which we're going to call mu, as usual, the population average, unknown population average. So here we go. First thing we're going to do is get a critical value for this 95%. However, because I don't know the population standard deviation, I'm going to be dealing with the sample standard deviation. I have to take this critical value from the t-distribution, because the t-distribution is the distribution of this statistic, which is what, if you think about the calculations that justify the confidence interval, that's what I'm working with, because I don't know sigma, I only know s. All right, so the t-distribution. So I'm looking for these critical values, which, to remind me that I'm working with the t-distribution, I'll call them t star and minus t star. So this critical value is going to be t star. And for 95% confidence interval, I want to figure out the number t star so that the area in between t star and minus t star is 95%. And in order to actually determine completely this distribution, I need this degree of freedom that changes its shape. So the degree of freedom here, remember, it's 1 less than the sample size. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, I said so. 10 randomly selected students, good. So the degree of freedom is 9. And once I set this degree of freedom, I will fix the shape of this distribution, and I should be able to, using a t-table, figure out these numbers. So this number t star, it's the number that has an area of what on its left? There's 5% left over, so 2.5% in each tail. So the area on the left here should be 0.975. So using a t-table, you should be able to come up with this critical value t star. It's the value here that has an area of 0.975 on its left. And I did that, and what did I get? I believe I got 2.26. Okay, yep. And now, from now on, that's really the only difference. The procedure is exactly the same. I'm just using the t-distribution in place of the standard normal distribution, and my margin of error formula, instead of having a z star here, is going to have a t star. Instead of having a sigma, it's going to have an s. It should be I guess a little s, because it's going to actually be a real number that I got from a single sample. Okay, good. So t star times s over root n. The t star I came up with is 2.26. The s, ooh. Well, the s, I have to actually calculate that using these values, right? So that is a big calculation. So the mean is easy enough. You add them all up and you divide by the number of values. And so I should say that, yeah, that from these values, I can do the calculations. And I just did them in Excel. So I came up with x bar equals 66.9. And I came up with, this is so messy, I'll just write it down here. Yeah, so let's rewrite here. So, yeah, I plop these values into Excel, and using Excel, I came up with x bar equals, what was it? I believe it was 66.9, and s equals 3.7478, sorry. So you should actually check that if you're going to compute this, not do it by hand, that you're really doing this Bessel-corrected standard deviation, where you're dividing by n minus 1 instead of n. So in Excel, it now, it defaults to that. I think the like STDEV formula defaults to that. And just to make it extra clear, they have these options, which maybe, I think at some point they decided you have to specify one or the other. Maybe not. Maybe you can still just say STDEV. But there'll be an STDEV.S, S for sample, or STDEV.P, P for population. And so if you're taking sample values and computing the standard deviation, then this STDEV.S will give you this Bessel-corrected standard deviation, where you divide by n minus 1 instead of by n. So I did that with Excel. I got this using average. I got this using STDEV.S. And then, away I go. I can compute the margin of error, just like I had before, t star times s over square root n. So 2.26 times 3.748 over root 10, 10 my sample size. And I came up with 2.46, 2.486. And now I have the margin of error, I have the sample mean, so I add and subtract the margin of error to the sample mean, and that gives me the confidence interval. So in this case, 95% confidence interval. So I can say, with 95% confidence, remember that means that there is a 95% probability of getting a sample that produces an interval that contains the mean, mu. So with 95% confidence, my sample mean mu is in the interval, what? Sample mean, 66.9. Add the standard deviation over here, and on the other side, take the sample mean, subtract the margin of error. So add and subtract the margin of error to the sample mean, and you come up with this confidence interval. I think I got 69, just correct to one decimal place, 69. So these are heights anyway. So, yeah. With 95% confidence, the average height of all students at the college is between 64.4 and 69.3 inches. Great. Now, quick discussion. I mentioned earlier that this thing only, in fact, this will only really have the t-distribution if you know you're sampling from a normally distributed population. And in this context, I don't know that. However, it turns out that if you look at human heights, they're not quite normally distributed, but they are close to normally distributed. It's still a kind of one bump distribution where the tails get really small really fast. And so even though my sample size is only 10, which is a very small sample size, the distribution of people's heights is very close to a normal distribution. And so it turns out that the distribution of this t statistic will be really close to a t distribution, and this the justification for this confidence interval is reasonably good. However, you should be aware that the smaller your sample size gets, and the further your population distribution is from being normal, the less accurate this will be. To really honestly have 95% confidence, that is 95% probability that a random sample will result in a confidence interval that contains the mean, you really have to satisfy all the assumptions, of course. But in here, this example, we're fine because we have this prior knowledge that it turns out the heights of human beings they're not quite normally distributed, but they have a sort of bell-shaped distribution, which makes things work out really well, both with the central limit theorem and also with this t statistic really, in fact, having the t distribution.